Tonight, we're going to fall into a black hole. Not as a thought experiment, not as an abstract physics lecture, but as a complete, honest, scientifically grounded account of what would actually happen to you. Step by step, moment by moment. From the first instant you cross the point of no return to the last possible second before the laws of physics themselves break down and stop making sense entirely. And by the end of tonight, you're going to understand something that very few people ever grasp. Falling into a black hole doesn't just mean dying. It means something far stranger than death. It means experiencing the most extreme physical events the universe is capable of producing. It means confronting a place where time itself stops being a line and starts being something else entirely. It means witnessing physics operating at the edge of what human understanding can reach, and then going past that edge. There are two versions of this story, your version and everyone else's version. And they are so different from each other that they seem to describe two completely unrelated events. We're going to tell both. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. Before we fall anywhere, we need to understand what we're falling into. Because most people's mental image of a black hole is wrong, and the wrong image will prevent you from understanding what actually happens. A black hole is not a hole. It is not an absence. It is not empty space. A black hole is one of the most extreme concentrations of matter in the universe. It is an object of enormous mass compressed into an extraordinarily small volume. And that compression creates a gravitational field so intense that not even light, the fastest thing in the universe, can escape from it once it gets too close. Let's trace the history. When a massive star, one with perhaps 10 or 20 or 30 times the mass of our Sun, exhausts the nuclear fuel in its core, the fusion reactions that have been supporting it against gravitational collapse stop. For millions of years, the outward pressure of nuclear fusion has been perfectly balanced against the inward pull of gravity. The star has been in equilibrium. When fusion stops, that equilibrium breaks instantly. Gravity wins. The outer layers of the star collapse inward at a fraction of the speed of light. They hit the dense inner core and bounce outward in a catastrophic explosion we call a supernova. The explosion can briefly outshine the entire galaxy, scattering the star's outer material across light years of space. The heavy elements it synthesized in its lifetime, the carbon, the oxygen, the iron, the gold, are returned to the universe to become the raw material of future stars and planets, and in some cases, living things. But the inner core, the remnant, continues to collapse. The protons and electrons that made up the original stellar material are crushed together into neutrons. For most massive stars, the collapse stops here. The neutrons resist further compression through a quantum mechanical pressure that prevents two neutrons from occupying the same quantum state. What remains is a neutron star, one of the densest objects in the observable universe, a sphere perhaps 12 miles across, containing a mass comparable to the Sun. For the most massive stars, even that quantum mechanical resistance is not enough. The weight of the overlying mass is too great. The collapse continues past the neutron star stage, past any threshold where our current physics can tell us what's happening inside. the matter compresses without any known mechanism to stop it. What results is a singularity, a point or region where the density of matter is effectively infinite and the curvature of space-time is infinite. The equations of general relativity, which otherwise predict the behavior of gravity with extraordinary precision, produce infinities at the singularity, division by zero. The equations break down. We don't know what happens at the center of a black hole because our physics stops working there. But surrounding that singularity is something we can describe precisely. A boundary. A surface defined not by any physical material, not by any wall or membrane or substance, but by geometry, by the curvature of space-time itself. This boundary is called the event horizon. The event horizon is the point of no return. It is the distance from the center of the black hole at which the escape velocity, the speed you would need to reach to escape the gravitational pull, exactly equals the speed of light. Inside the event horizon, the escape velocity exceeds the speed of light. Since nothing can travel faster than light, nothing inside the event horizon can escape. Not light, not radiation, not information of any kind. This is why black holes are black, not because they absorb light like a dark surface absorbs light, but because light that enters within the event horizon cannot come back out. Light that grazes the event horizon from the outside is bent and distorted, but eventually escapes. Light that crosses the horizon is trapped forever. The radius of the event horizon, called the Schwarzschild radius after the physicist Carl Schwarzschild, who first calculated it in 1916, depends on the mass of the black hole. For an object with the mass of the Sun, the Schwarzschild radius is about 3 kilometers. The entire mass of the Sun, compressed into a sphere 6 kilometers across, would become a black hole. Our Sun will never actually become a black hole, because it's not massive enough. But the calculation tells us the relationship between mass and event horizon size. For more massive black holes, the event horizon is correspondingly larger. A black hole with a mass 10 times the Sun has an event horizon about 30 kilometers across. A black hole with a mass 1 million times the Sun, common at the centers of smaller galaxies, has an event horizon several million kilometers across. The supermassive black hole at the center of our own galaxy, Sagittarius A star, has a mass of about 4 million solar masses and an event horizon with a radius of roughly 12 million kilometers, larger than the orbit of Mercury around the Sun. And then there are the true giants, the supermassive black holes at the centers of the most active galaxies. Quasars and active galactic nuclei can reach masses of billions of solar masses. The largest known black hole, TON 618, has a mass of about 66 billion solar masses. Its event horizon would swallow our entire solar system many times over. It is toward one of these objects, enormous and ancient, that we are falling tonight. You are in space, not on a spacecraft, not in a suit. In this thought experiment, you simply exist in space, near enough to the black hole to see it, far enough to still be in the realm of physics that makes sense. What do you see? This is where reality immediately diverges from the science fiction image. A black hole does not look like a swirling blue or purple funnel with a bright center. It doesn't look like a drain in a bathtub. A real black hole seen against the background of space looks like a perfect black circle surrounded by a ring of extraordinary brightness. That ring is the accretion disk and the photon sphere. Let me explain both. Black holes in the real universe are rarely isolated objects floating in perfect emptiness. They have material falling into them: gas, dust, the shredded remnants of stars that wandered too close. This material doesn't fall straight in. It has angular momentum, a tendency to orbit rather than plunge directly. So it forms a disk of spiraling material around the black hole, called an accretion disk. As this material spirals inward, it is compressed and heated by friction and magnetic forces to temperatures of millions of degrees. At these temperatures, it radiates across the electromagnetic spectrum from radio waves through visible light to X-rays and gamma rays. Some of the most luminous objects in the observable universe are not stars, but the accretion disks around supermassive black holes, active galactic nuclei, and quasars blazing with more light than entire galaxies. The accretion disk glows intensely, and because of the extreme curvature of space-time near the black hole, the light from the far side of the disk is bent around the black hole, and you can see it appearing above and below the black circle of the event horizon. This creates the glowing ring effect: bright above, bright below, with the completely black circle of the event horizon at the center. This is almost exactly what the Event Horizon Telescope captured in 2019, the first real photograph ever taken of a black hole. The image showed Messier 87 star, the supermassive black hole at the center of the galaxy M87, 55 million light-years away, a black circle surrounded by an orange-white glowing ring, brighter on one side where the material is moving toward us, and dimmer on the other side where it's moving away. A real black hole photographed for the first time in human history. And it looked almost exactly as the equations of general relativity had predicted it would look for over a century. The photon sphere is a region where the curvature of space-time is so extreme that light can orbit the black hole. Photons moving at exactly the right angle at exactly the right distance are caught in a perpetual loop, circling the black hole indefinitely. This creates a bright ring of trapped and circling light, visible to observers at certain angles. The photon sphere is not a stable orbit. Photons perturbed slightly inward spiral into the black hole. Photons perturbed slightly outward eventually escape. But at that precise radius, they orbit forever, in theory. As you fall toward the black hole, these visual effects become more pronounced. Space-time bends more severely. Light from behind you is bent around the black hole and appears in front of you. Stars that should be hidden behind the black hole appear around its edges. The entire universe you see behind you is compressed into a shrinking circle ahead and around you as you fall deeper into the gravitational well. The black hole seems to grow to fill more and more of your field of view. And you begin to notice something else. Stars near the black hole appear to shift in color. Stars ahead of you, in the direction you're falling, appear bluer. Their light is being blue shifted, compressed to shorter wavelengths as you fall into the gravitational field toward them. Stars behind you appear redder. Their light is being red shifted, stretched to longer wavelengths as you move away. You are, at this point, still outside the event horizon. The tidal forces, the difference in gravitational pull between your head and your feet, are not yet lethal. If this is a large enough black hole, a supermassive giant with millions or billions of solar masses, the tidal forces at the event horizon are actually quite gentle, comparable to the gravitational gradient you'd experience sitting in a chair on Earth. This is one of the most counterintuitive things about black holes, and we'll come back to it. But you are accelerating, falling. And the fall is not what you'd feel standing in a gravitational field. You are in free fall, which means you feel no weight, no force pressing you down, no sensation of being pulled, just weightlessness, like an astronaut in orbit, like floating in space. The extreme gravity of the black hole is not something you feel directly in the way you'd feel your weight on the ground. You feel the consequences of that gravity. Things around you are doing strange things. Space-time is distorted. Light is bending. But you yourself feel nothing unusual yet. This matters. It matters because it means that the moment you cross the event horizon will not feel like anything special from your perspective. That's one of the most profound things about black holes. Let's pause here because we need to establish something fundamental before we cross the horizon. When you fall into a black hole, there are two completely different accounts of what happens. Two stories. Both are true. Both are consistent with the laws of physics. But they describe such different events that they seem contradictory. Understanding both, and understanding why they can both be true simultaneously, is one of the deepest insights you can have about the nature of reality. The first story is your story. The story from your perspective. The perspective of someone falling into the black hole. The second story is the story from the perspective of a distant observer. Someone watching you fall from far away. Someone sitting safe in a spacecraft 1,000,000 kilometers from the event horizon, watching through a telescope. These two stories are so different that physicists spent decades arguing about which one was the real story. The answer, which we'll explore in detail, is that they're both real. The apparent contradiction between them reveals something fundamental about the nature of space-time that has no analog in everyday experience. Let's start with your story. Part 4. Your story. Crossing the horizon. From your perspective, as you fall freely toward the black hole, something happens and something doesn't happen. What doesn't happen? You don't feel anything special when you cross the event horizon. There is no wall, no barrier, no flash of light, no alarm sounds. You pass through what is, from your perspective, apparently empty space. The event horizon is not a physical object. It's a boundary defined by the geometry of space-time, and that geometry doesn't announce itself with any local physical signal. If the black hole is large enough, the tidal forces at the horizon are negligible, and you cross the boundary without noticing anything unusual. This is actually one of the most profound implications of general relativity. The equivalence principle. The idea that gravity and acceleration are locally equivalent means that a freely falling observer in a gravitational field experiences no force. You feel weightless. You feel fine. You cross the horizon. What does happen? Once you cross the event horizon, the singularity is in your future. This sounds like ordinary language, but it has a technical meaning. In the curved space-time geometry inside a black hole, The singularity is not just at the center of the black hole in the spatial sense. It is in the future of every path through space-time inside the event horizon. No matter which direction you move, no matter what you do, the singularity is where you end up. It's not like a wall you hit when you reach the center. It's more like tomorrow, something you cannot avoid, regardless of what you do, because all paths through space-time lead there. You're now inside the event horizon. You continue falling. The black hole's interior, despite what you might expect, is not dark. Well, it's complicated. If the black hole has an accretion disk, some of that light is falling in along with you. The inside of the event horizon is not a place without light. It's a place without escape. As you fall inward, you can still see light from outside the black hole, though increasingly distorted. You can see the accretion disk. You can see the universe outside, compressed into an increasingly small circle of light in one direction, as the curvature of space-time increasingly confines what you can see. The tidal forces are growing. Remember how I said the tidal forces at the horizon of a supermassive black hole are gentle? That's true at the horizon. But as you fall inward, toward the singularity, tidal forces increase. How quickly they increase depends on the mass of the black hole. For a smaller black hole, a stellar mass black hole of perhaps 10 solar masses, with an event horizon only 30 kilometers across, the tidal forces become lethal before you even cross the horizon. For a sufficiently massive giant, they remain tolerable for some time after you've crossed. But they grow. The tidal force, the difference in gravitational pull between your head and your feet, or between any 2 points separated along the direction toward the singularity, increases as you fall deeper. Eventually, and this happens at a different time for different mass black holes, the tidal force becomes strong enough to pull you apart. Your body, the distance between your head and your feet, experiences significantly different gravitational pulls. The difference stretches you in the direction you're falling, while compressing you from the sides. Physicists call this process spaghettification. The name is accurate and undignified. You are stretched like taffy, like pasta being pulled from a dough, elongated and compressed simultaneously. First into a somewhat elongated shape, then into a thinner and thinner strand. The process happens faster and faster as you approach the singularity because the gravitational gradient increases without limit. At some point during this process, you stop being recognizable as a person. The atoms that made you are still there, still governed by physics. But the structure that made you human, the intricate organization of cells and molecules and consciousness, has been destroyed by the increasing tidal forces. What happens to those atoms as they approach the singularity? Here is where your story reaches a point where physics itself admits it doesn't know the answer. As the density of matter approaches infinite and the curvature of space-time approaches infinite near the singularity, the equations of general relativity produce infinities. Division by zero. Meaningless results. The theory we have to describe gravity, our best and most thoroughly tested theory of space-time and gravity, stops working at the singularity. It breaks down. It produces predictions that are not physically meaningful. This tells us one of two things. Either the singularity is genuinely a place where the usual laws of physics are suspended and something genuinely physically infinite occurs, which would be extraordinarily strange. Or more likely, the equations are telling us that general relativity itself breaks down as a description of nature at these extreme conditions, and that a more complete theory, one that combines general relativity with quantum mechanics, would give us finite, meaningful predictions even at the singularity. We don't have that more complete theory yet. Physicists call it quantum gravity, and its development is one of the central unsolved problems in theoretical physics. String theory is one attempt. Loop quantum gravity is another. Several other approaches exist. None has been experimentally confirmed. None has been fully worked out. What happens at the singularity is genuinely unknown. What we can say is this: in the framework of general relativity, the singularity is the end of all paths. Every trajectory inside the event horizon terminates at the singularity. The singularity is the future, and the future inside the event horizon ends there. In a quantum theory of gravity, this might be different. The singularity might be resolved into something less extreme, something finite, something where the laws of physics remain meaningful all the way through. Some physicists believe this. Some believe the singularity itself is avoided in a quantum treatment. We don't know. From your perspective, falling into a black hole, you cross the horizon without noticing, experience increasing tidal forces, are spaghettified, and approach the singularity. The experience from your own frame of reference takes a finite time. For a stellar mass black hole, the journey from the horizon to the singularity takes a fraction of a second. For a supermassive black hole with billions of solar masses, it might take hours or even days. But it ends. It ends at the singularity, where our physics breaks down. That is your story. Now let's tell the other one. A friend of yours is sitting in a spacecraft 1 million kilometers from the black hole, safe, far outside the event horizon, watching you fall through a telescope. What do they see? This is where the story becomes so strange that it seems impossible. But the physics is unambiguous and has been confirmed through numerous indirect tests and observations. Your friend watches you fall toward the black hole. As you approach the event horizon, they see you falling slower. Not because you're actually slowing down. From your perspective, you're in free fall, accelerating continuously, feeling nothing unusual. But the light you're emitting as you fall is being increasingly red-shifted as it climbs out of the increasingly deep gravitational well of the black hole. Remember what redshift means. Light is a wave. Gravity stretches waves as they climb out of a gravitational field. The frequency drops. The energy decreases. The light shifts toward longer wavelengths, toward the red end of the spectrum and beyond. As you approach the event horizon, the light you emit is more and more red-shifted. From your friend's perspective, you appear to be moving more and more slowly. The light from your earlier position takes less time to reach them. The light from your later, closer position has to climb out of a deeper gravitational well, losing energy, taking effectively longer to arrive. The intervals between the light pulses they receive from you become longer and longer. There's something else. As light climbs out of the gravitational field of the black hole, it also experiences time dilation. Gravitational time dilation is real, measurable, and enormously consequential near a black hole. Time runs slower in a stronger gravitational field. The light you emit when you're close to the event horizon was emitted by you at a moment when time, for you, was running slower relative to your distant friend. The combination of these effects means that, from your friend's perspective, you appear to slow down asymptotically as you approach the event horizon. You appear to move more and more slowly. The light from you is more and more red-shifted. You appear to get dimmer and dimmer as the red-shifted light carries less and less energy. You never appear to cross the horizon. From your friend's perspective, you asymptotically approach the event horizon, slowing to a crawl, fading to red, and effectively freezing just outside the horizon, becoming so dim and so red-shifted that eventually no light from you reaches them at all. You never appear to cross. You appear to freeze. Forever. This is not an illusion. This is not just an effect of the travel time of light. This is a genuine consequence of how space-time is curved near a black hole. From the perspective of a distant observer, the event horizon is not a place you can reach in a finite time. The gravitational time dilation is infinite at the event horizon. Infinite time dilation means infinite redshift. Infinite time means the clock at the event horizon runs infinitely slowly from the outside perspective. From outside, the event horizon is a place where time stops. It is a boundary where, from an external perspective, all events are frozen and infinitely red-shifted. And yet from your perspective, you cross it in finite time and nothing unusual happens. Both are true. Both are descriptions of the same physical events from different reference frames. General relativity is the mathematical framework that allows both to be simultaneously true and consistent. This is not just theory. We have measured gravitational time dilation directly. Atomic clocks at different altitudes on Earth run at measurably different rates. The GPS satellites that provide navigation to billions of people require corrections for both gravitational time dilation and the time dilation due to their velocity. Without those corrections, GPS accuracy would degrade by kilometers per day. Gravitational time dilation is real, measured, and used in technology you rely on every day. Near a black hole, the same phenomenon operates at infinitely more extreme levels. Here is where the two stories create a problem so severe that it has occupied some of the greatest physicists alive for decades. You cross the event horizon. From your perspective, fine. From your friend's perspective, you freeze at the horizon and slowly fade away. But what happens to the information that made you, you? The specific arrangement of atoms, the quantum states of every particle that constituted your body and your memory and your consciousness. In quantum mechanics, information is conserved. This is not a minor technical point. This is one of the fundamental principles of quantum physics. The laws of quantum mechanics are time reversible. If you know the precise quantum state of a system at any moment, you can calculate what it will be at any future time and what it was at any past time. Information is never destroyed. It's one of the bedrock principles of how the universe operates at the quantum level. But if you fall into a black hole, your information falls in with you. The information about your specific quantum state, the information that makes you different from any other arrangement of matter, enters the event horizon and, in the classical description, reaches the singularity and is destroyed. And here's the second part of the problem. Stephen Hawking showed in 1974, using a calculation that combined general relativity with quantum field theory. The black holes radiate. They emit thermal radiation, now called Hawking radiation. This radiation is produced by quantum effects near the event horizon, where the extreme curvature of space-time causes pairs of virtual particles to be created, one particle falling inward and one escaping. This process gradually drains energy from the black hole. Over astronomical timescales, the black hole loses mass and eventually evaporates completely. Hawking radiation is thermal radiation. It's random. It carries no specific information about what fell into the black hole. If your friend waits long enough, they'll watch the black hole slowly evaporate through Hawking radiation until nothing is left except that random thermal glow. And the information about you, the information that specified your exact quantum state when you fell in, is gone, permanently destroyed. This is called the black hole information paradox, and it is one of the deepest unsolved problems in theoretical physics, because quantum mechanics says information cannot be destroyed. And yet, if we combine general relativity and quantum field theory in the way Hawking did, information appears to be destroyed in black holes. Either quantum mechanics is wrong about information being conserved, which would require a fundamental revision of our most successful and precisely tested physical theory, or general relativity is wrong about something that happens at or near the event horizon, or our combination of the two theories is missing something important, which is likely since we don't have a complete quantum theory of gravity. The debate has produced some of the most creative and intense theoretical work in physics over the past 50 years. One proposed resolution, still speculative and debated, is that the information is somehow encoded in the Hawking radiation, not randomly, but in subtle correlations that are so complex they appear random, but actually carry the full information about what fell in. This is called the unitarity of black hole evaporation, and it's the view that most quantum information theorists favor because it preserves quantum mechanics. But the mechanism by which information gets encoded in the radiation and how it escapes the event horizon to do so is deeply unclear. Another proposed resolution is related to the firewall paradox, proposed in 2012 by Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, which showed that preserving quantum information leads to a contradiction with the idea that nothing unusual happens when you cross the event horizon. If information is preserved, they argued, then there must be a firewall of high-energy radiation at the event horizon that destroys anything crossing it, contradicting the smooth crossing that general relativity predicts. The firewall debate has been one of the hottest controversies in theoretical physics since it was proposed. A more recent approach involves what are called islands and replica wormholes, a framework developed in the last few years that seems to show how information can be preserved in principle. Though the physical mechanism remains unclear, and the mathematics is highly formal and difficult to interpret physically, the black hole information paradox is, as of the time of this writing, unresolved. We don't know the answer. Some of the most brilliant physicists in the world have spent careers on it and have not reached consensus. What we do know is that it's pointing us towards something fundamental. The combination of gravity and quantum mechanics produces contradictions that our current theories cannot resolve. Resolving those contradictions will require new physics. And that new physics, whatever it turns out to be, will almost certainly reshape our understanding of space, time, information, and reality in ways we can't fully anticipate. The black hole is not just an exotic object. It's a laboratory for testing the deepest questions about the nature of reality. And we fall into it without knowing whether the information of what we are survives. Let's return to your experience inside the event horizon. Because while the philosophical and physical questions are profound, the physical experience of spaghettification deserves more attention. It's one of the most extreme processes in the universe, and it happens to you step by step in a way we can describe precisely. Tidal forces arise from the difference in gravitational pull across an extended object. When you're standing on Earth, your feet experience slightly more gravitational pull than your head because they're closer to Earth's center. The difference is tiny and unmeasurable by any sensation you have. But the principle is universal. Near a black hole, this difference grows. Your feet, if you're falling feet first, are pulled more strongly than your head. The difference in gravitational pull creates a net stretching force along the direction toward the singularity. Simultaneously, from the sides, the gravitational pull across your body, which is directed slightly inward from each side because both sides of your body are being pulled toward the same point, creates a compressive force perpendicular to your direction of motion. Think of it this way. Imagine you're holding a rubber band with both hands. If you pull your hands apart, the band stretches. Your body in a tidal gravitational field experiences something similar. The part of you closest to the singularity is pulled harder than the part farther away. The difference in force stretches you. For small black holes, stellar mass objects of 10 to 40 solar masses, with event horizons measured in tens of kilometers, the tidal force at the event horizon is already overwhelming. The gravitational gradient from head to foot across a distance of 2 meters is already many millions of times greater than what you experience on Earth's surface. You would be spaghettified before you crossed the horizon, somewhere outside it, in the last moments of approach. For a supermassive black hole with millions of solar masses and an event horizon millions of kilometers across, the gravitational gradient at the event horizon is much gentler, comparable in scale to the tides on Earth. You cross the horizon intact. The tidal forces are there, slightly greater pull on your feet than your head, but not yet dangerous. You survive crossing the horizon. But as you fall deeper toward the singularity, the tidal forces increase with the inverse cube of your distance from the center. If the black hole is 1 million solar masses, you might survive several hours after crossing the event horizon before the tidal forces become lethal. If it's 1 billion solar masses, perhaps days. But the outcome is the same. The tidal forces eventually exceed the tensile strength of your body's tissues, and the process begins. It starts in the softest, weakest structures. Fluids shift and tear. Organs are distorted. Then the cellular structures, the membranes and connections holding cells together, are stretched beyond their elastic limits. Then the cells themselves. Then molecular bonds. Then, as the singularity approaches and the gravitational gradient becomes still more extreme, even atomic structures are distorted. The electrons in their orbitals experience different forces than the nuclei they orbit. Eventually, even atomic nuclei, the protons and neutrons tightly bound by the strong nuclear force, experience tidal forces comparable to nuclear binding energies. You are not spaghettified into a long string all at once. It's a gradient. The part of you nearest the singularity is most distorted, most stretched. The process propagates through you from the end closest to the singularity outward. You are drawn out, elongated, and compressed from the sides into a progressively thinner and longer strand. The physics of what happens to the material at the quantum level near the singularity is, as we discussed, unknown. At some point before the singularity, the energy densities involved exceed anything our tested theories can describe. The laws of physics, as we know them, stop applying. What actually happens there is one of the great open questions. But the spaghettification process is not mysterious. It follows directly from the mathematics of general relativity and the structure of the gravitational field. It is, in a physics sense, well understood, even if experientially extreme. And there's one more thing about spaghettification that is important to understand. It doesn't happen instantaneously. There is a period during which you are being stretched and compressed, but not yet destroyed. If you have any capacity to observe what's happening during this period, the view would be extraordinary. The light from outside the event horizon, visible through a shrinking circle ahead, would show an increasingly distorted universe. The entire sky behind you compressed into that circle. The light blue shifted by your increasing infall velocity. Time outside appearing to run faster and faster as the gravitational time dilation inside becomes more extreme relative to the outside. In your last moments, you would be watching the future of the universe rush past. Events that would take billions of years outside the black hole appearing to happen in compressed time as you approach the singularity. This is another of the profound and deeply strange consequences of the geometry of black hole spacetime. We mentioned Hawking radiation earlier in the context of the information paradox. Let's understand it more deeply, because it changes everything about what we thought black holes were. Before Stephen Hawking's 1974 calculation, black holes were thought to be perfectly cold in the thermodynamic sense. They absorbed everything and emitted nothing. No radiation, no heat, no light. Perfect thermal blackbodies with temperature precisely zero. An event horizon was the ultimate absorber. In classical general relativity, this is exactly right. But quantum mechanics complicates everything. In quantum field theory, the vacuum is not empty. Empty space is filled with quantum fields, the underlying mathematical structures that describe all particles and forces. These fields fluctuate at the quantum level. Even in a perfect vacuum with no particles present, the fields are vibrating. These fluctuations give rise to what are called virtual particles, pairs of particles, and their antiparticles that spontaneously appear and then annihilate within the limit allowed by the uncertainty principle. This sounds like magic, but it has real physical consequences. The Casimir effect, the attraction between two uncharged metal plates held close together in a vacuum, is a measured consequence of vacuum fluctuations. It's been confirmed in laboratories. The vacuum is real. It fluctuates. And those fluctuations have physical effects. Near the event horizon of a black hole, the extreme curvature of space-time affects these vacuum fluctuations in a specific way. Pairs of virtual particles are created near the horizon. In most of empty space, both particles annihilate each other almost immediately. But at the event horizon, it becomes possible for one particle of the pair to fall inside the horizon while the other escapes outward. When this happens, the particle that escapes becomes real, no longer a virtual particle that must annihilate, but a real particle that carries real energy away from the black hole. The energy has to come from somewhere. It comes from the gravitational energy of the black hole itself. The black hole loses mass. It radiates. The spectrum of this Hawking radiation, the distribution of energies of the emitted particles, is exactly thermal. It follows the same mathematical distribution as the radiation from a perfect black body at a specific temperature. The temperature of this radiation depends on the mass of the black hole. Specifically, the Hawking temperature is inversely proportional to the mass. A more massive black hole has a lower Hawking temperature. For a solar mass black hole, the Hawking temperature is approximately 60 billionths of a Kelvin, a temperature so close to absolute zero that it is colder than the cosmic microwave background radiation that fills all of space. Such a black hole absorbs more energy from the microwave background than it radiates through Hawking radiation. It grows, not shrinks. For a much smaller black hole, the Hawking temperature is higher. A black hole with a mass of about 100 billion tons, roughly the mass of a mountain, would have a Hawking temperature of about 1,000 billion Kelvin, and to be radiating at an enormous rate, evaporating quickly. Such small black holes, if they exist, might be detectable as sources of gamma rays. As a black hole evaporates through Hawking radiation, its mass decreases. As its mass decreases, its temperature increases. As its temperature increases, it radiates more intensely. This is a runaway process. In the final moments of a black hole's evaporation, it becomes extremely hot, extremely small, and radiates with explosive intensity. The final evaporation is thought to be an explosion of high-energy particles and radiation. Though the details depend on quantum gravity physics we don't fully understand. The timescale for evaporation of a stellar mass black hole is approximately 10 to the power of 74 years. That number has 74 digits. It is so far beyond the current age of the universe, 13.8 billion years, that no stellar mass black hole formed today will evaporate for an almost incomprehensibly long time. The universe would have to age by many orders of magnitude beyond its current state before any black hole evaporated. But eventually, given enough time, they all evaporate. Every black hole in the universe, given sufficient time, will radiate itself away into Hawking radiation and cease to exist. And when the last black hole has evaporated, what is left? The Hawking radiation, thermal, spread throughout space, cooling as the universe continues to expand. And if the information paradox is resolved, somehow encoding in its subtle correlations the quantum states of everything that ever fell into every black hole that ever existed. We don't know if that's true, but it's one of the deep hopes of theoretical physics. Not all black holes are the same. We've been talking primarily about two types: stellar mass black holes formed from collapsing stars, and supermassive black holes at the centers of galaxies. But the family of black holes is broader and stranger than that. Stellar mass black holes range from about 3 solar masses, the minimum mass for a black hole below which neutron star matter can resist collapse, to about 100 solar masses for the most massive stellar black holes observed. They are formed either by the collapse of massive individual stars or by the merger of neutron stars. In September 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made the first direct detection of gravitational waves. The signal came from the merger of 2 black holes, one with about 36 solar masses and one with about 29, at a distance of about 1.3 billion light-years. The merger released energy equivalent to 3 solar masses in gravitational waves in a fraction of a second, producing a signal that distorted space-time by a distance less than 1,000th of the diameter of a proton as it passed through Earth. And LIGO detected it. That detection confirmed general relativity's prediction of gravitational waves and opened a new window on the universe. Intermediate mass black holes, with masses between 100 and 1,000,000 solar masses, are thought to exist but are less well established observationally. They may form through the merger of stellar mass black holes in dense environments, or through the direct collapse of massive gas clouds in the early universe. Supermassive black holes, ranging from millions to tens of billions of solar masses, reside at the centers of virtually all large galaxies. Their origin is one of the open questions in astrophysics. How do black holes of millions or billions of solar masses form? Did they grow gradually through accretion over billions of years? Did they form from the direct collapse of massive primordial gas clouds in the early universe? Were they seeded by early massive stars? We don't know with certainty. And then there are primordial black holes, a hypothetical class that might have formed in the extremely dense early universe, shortly after the Big Bang, from density fluctuations in the primordial plasma. These have not been confirmed observationally, but they remain an active area of theoretical interest. Some physicists have proposed that primordial black holes in a certain mass range could account for some or all of the dark matter in the universe, the invisible mass that makes up most of the gravitational content of galaxies, but whose nature remains unknown. Rotating black holes, called Kerr black holes after Roy Kerr, who found the solution in 1963, are more realistic than the simple non-rotating Schwarzschild black holes we've been discussing. When a massive object collapses to form a black hole, it brings its angular momentum with it. Conservation of angular momentum ensures that the black hole rotates, and rotation changes the geometry of space-time around it profoundly. A rotating black hole doesn't just have an event horizon. It has an ergosphere, a region outside the event horizon where space-time itself is dragged along by the black hole's rotation. Inside the ergosphere, it's impossible to stand still relative to the distant stars. Space-time itself is rotating, dragging everything with it. Objects in the ergosphere can still escape the black hole. They haven't crossed the event horizon. But they cannot remain stationary. The ergosphere enables a process called the Penrose process, proposed by Roger Penrose in 1969. In the ergosphere, it's possible in principle to extract rotational energy from the black hole. An object entering the ergosphere splits into 2 parts. One part falls into the event horizon with negative energy relative to a distant observer, while the other escapes with more energy than the original object had. The extra energy comes from the black hole's rotational energy. The black hole slows its rotation slightly. Given enough such processes, the black hole's rotation is reduced. The Penrose process provides a theoretical mechanism for extracting energy from black holes, and it's been proposed as a possible power source for advanced civilizations or as a mechanism for astrophysical jets. The enormous beams of material that many black holes shoot outward along their rotation axes. The jets from active galactic nuclei and quasars are among the most powerful phenomena in the universe. Beams of plasma accelerated to nearly the speed of light and extending for millions of light years into surrounding space. The exact mechanism is still debated, but magnetic fields threading through the ergosphere and driving material outward along the rotation axis is a leading model. Black holes don't just consume, they also produce dramatically through these outflows. Charged black holes, called Reisner-Nordström black holes, form another theoretical class. An electrically charged black hole would have a different space-time geometry than an uncharged one. In theory, inside a charged black hole, there is a region called the inner horizon, where the gravitational singularity doesn't behave like the one in an uncharged black hole. There are theoretical solutions in which you could, in principle, pass through the inner horizon and emerge in a different region of space-time, essentially a traversable passage to another location or another time. These charged black hole solutions are fascinating mathematically, but charged black holes almost certainly don't exist in nature. Any charged black hole would rapidly attract the opposite charge from surrounding matter, neutralizing itself almost immediately. The universe provides no shortage of charged particles. Real black holes are effectively electrically neutral. Rotating black holes with their ergospheres and the rich structure of Kerr spacetime are far more physically relevant, and they contain something analogous to the inner horizon that raises similar questions about the physical nature of singularities in rotating spacetimes. These questions connect to deep issues in general relativity that remain unresolved. Let's go back to falling. Because there's one more aspect of your experience inside the event horizon that we haven't addressed. Something that is both physically precise and profoundly strange. Inside the event horizon, the coordinate traditionally called the radial direction, the direction pointing toward and away from the center of the black hole, becomes time-like. This is technical language, but it has a concrete meaning. In the space-time geometry outside a black hole, you can choose to move in any direction in space. You can go left or right, forward or backward, up or down. You have freedom in spatial directions. The future is fixed. Time always moves forward. You can't reverse time, but you can choose your spatial path. Inside the event horizon, this changes. The radial direction, toward and away from the singularity, becomes time-like. Moving away from the singularity inside the event horizon is like moving backward in time outside it. It's not possible. Just as you cannot move backward in time outside the black hole, no matter how hard you try, you cannot move away from the singularity inside it. Every path forward in time inside the event horizon leads toward the singularity. The singularity is your future. not a place you will reach when you travel far enough in a certain spatial direction, but a moment in time, a point in your future that is unavoidable, like tomorrow. This is what it means to say that inside the event horizon, the future points toward the singularity. Space and time inside a black hole have swapped roles. What was a spatial direction toward the center has become a temporal direction toward the future. What was the future direction in time outside has become a spatial direction inside. The mathematics is precise. The consequence is absolute. You cannot avoid the singularity by any spatial maneuvering, any more than you can avoid tomorrow by standing still. And the singularity, that endpoint that our equations cannot describe, represents the edge of our understanding, not just of physics, but of what physical description even means. The mathematical structure of general relativity reaches its own boundary there. The universe, or at least the universe our best theories can describe, ends at the singularity. Beyond that, we don't know. We genuinely, honestly don't know. This is not the false modesty of a scientist hedging their bets. This is the real limit, the place where our understanding stops. We have clues from quantum gravity approaches. We have theoretical speculation. We have mathematical structures that might point toward answers. But we don't have the answer. Falling into a black hole is falling toward the edge of what physics knows, and then past it. In your final moments inside the event horizon, approaching the singularity, something extraordinary is happening to your perception of the outside universe. Light from the external universe is still reaching you, but it's arriving with increasing frequency and energy as you fall deeper into the gravitational field. The blue shift increases. Light that was visible is now ultraviolet. Ultraviolet becomes X-ray. X-ray becomes gamma ray. The energy of the light from outside is climbing rapidly, and the direction from which that light comes is increasingly compressed. The entire external universe appears to come from an increasingly small region directly above you, directly away from the singularity. The universe outside is compressed into a bright, shrinking, increasingly energetic point. Simultaneously, the time you can perceive from outside the black hole is accelerating. As your proper time slows relative to the outside universe, you see external events time dilated, apparently running faster. The entire history of the external universe is, in principle, compressed into the remaining time of your fall. Whether you could actually perceive this, whether your sensors or your biology could register these effects before spaghettification destroys the structures necessary for perception, depends on the specific parameters. For sufficiently large black holes, you might survive long enough after crossing to perceive some of these effects. For smaller ones, the spaghettification happens too fast. But the physics is there. The universe outside runs faster as you run out of time inside. This is one of the most extraordinary aspects of falling into a black hole. The external universe doesn't disappear. It appears to compress, to speed up, to ultimately contain all of future time in the moments before the singularity. Whether anything in the universe lasts forever is another open question. If the universe eventually reaches heat death, with no remaining temperature differences, no remaining energy gradients, nothing left to observe or do, then the future of the universe, visible from inside the black hole, is finite. There's only so much future to compress. But in principle, the geometry of the situation is as I've described. Inside a black hole, the entire future of the external universe is, geometrically, accessible to an observer, falling toward the singularity. Everything that will ever happen outside is in your past light cone inside. You can receive information from the entire future of the universe in your remaining time before the singularity. This is deeply strange, and we don't fully know what to make of it physically, especially given that the universe continues for what may be an essentially infinite amount of time, and the singularity terminates your path in a finite amount of your time. Quantum gravity may resolve this. The singularity may not really be a termination of all paths. In some quantum gravity frameworks, the singularity is replaced by a bounce, a point of maximum density, where the trajectory reverses and passes through into a new region of space-time. Whether that new region is an extension of our universe or something else entirely is unknown. But in classical general relativity, the singularity is the end. Let's pull back from the interior of the black hole and think about what this thought experiment has shown us. Falling into a black hole is not a story about death, though it ends in that. It's a story about the nature of space and time, about the limits of physical description, about the relationship between different observers of the same events, about the deepest questions in modern physics. It shows us that time is not absolute. Different observers experience time at different rates depending on their velocity and position in a gravitational field. This is not philosophy or metaphor. It's measured fact, demonstrated with atomic clocks and GPS satellites and astronomical observations. Near a black hole, this effect is taken to its extreme limit. It shows us that information, what makes you you, is at the heart of the deepest unresolved tension in theoretical physics. We don't know if information is conserved in black hole evaporation. We don't know if the quantum mechanical principle that information cannot be destroyed survives contact with strong gravitational fields. Resolving this question is one of the most urgent tasks in fundamental physics. It shows us that our two best theories of the universe, general relativity and quantum mechanics, are in tension with each other in the extreme environment of a black hole. This tension is productive. It's a clue. It's pointing toward new physics, toward a deeper theory that unifies gravity and quantum mechanics in a way that resolves the contradictions. Whatever that theory is, it will transform our understanding of reality. It shows us that the universe contains extremes we have barely begun to understand. Places where space-time is torn apart, where temperature reaches effective infinity, where matter is compressed to infinite density, and our equations give up trying to describe it. The universe is not a comfortable place, scaled to human intuitions and human limits. It is vast, violent, extreme, and beautiful in its extremity. And it shows us something about knowledge itself. We can calculate with extraordinary precision what happens as you approach the event horizon. We can describe the gravitational lensing, the time dilation, the Hawking radiation, the trajectory of light, the curvature of space-time. All of this is understood with remarkable depth and precision. And then there's the singularity, where all that precision fails, where our equations break down, where the universe is doing something we can't yet describe. The boundary between what we know and what we don't is one of the most important places in science. It's where the next revolution in understanding begins. Black holes sit squarely on that boundary. Let's take a broader view, because individual black holes are extraordinary. But black holes as a class of objects have shaped the universe in ways that go far beyond what any single one can do. The supermassive black holes at the centers of galaxies are not passive objects sitting there being extreme. They are active agents in the structure and evolution of galaxies. During their active phases, when they're consuming material at high rates and their accretion disks are blazing with light, they can outshine entire galaxies containing hundreds of billions of stars. These are the quasars and active galactic nuclei, the most luminous objects in the observable universe. But the influence extends beyond light. The jets of plasma that many active black holes produce, accelerated to nearly the speed of light along the rotation axis, can extend for millions of light years and carry enormous energy into the surrounding galactic medium. These jets heat the gas in and around galaxies. They can suppress star formation by heating gas that would otherwise cool and collapse into new stars. They can trigger star formation by compressing cool gas with their shock waves. The feedback between supermassive black holes and the galaxies they inhabit is a key driver of galactic evolution. We would not have the universe we do, the distribution of galaxies and their properties, without the feedback from supermassive black holes over cosmic time. Gravitational waves from merging black holes, now detectable by LIGO and Virgo and Kagra, are a completely new window on the universe. Before 2015, all our information about the universe came from electromagnetic radiation, neutrinos, and cosmic rays, forms of energy that can be absorbed, scattered, and distorted by the matter they pass through. Gravitational waves pass through essentially everything. They carry direct information about the space-time geometry of their sources, unobscured. We are now hearing the universe in a new way. The population of binary black hole mergers detected since 2015 has revealed a surprising diversity of black hole masses and merger rates, challenging some theoretical predictions and opening questions about the formation of massive black holes through stellar and dynamical processes. Future gravitational wave detectors, space-based observatories like LISA planned for the 2030s, will be sensitive to gravitational waves from merging supermassive black holes across the observable universe. They will let us map the merger history of galaxies across cosmic time, directly observing the processes that built the large-scale structure of the universe. And there's the Event Horizon Telescope, which produced the first image of a black hole shadow in 2019 and has since imaged Sagittarius A star, the black hole at the center of our own galaxy. These images are direct tests of general relativity in the strongest gravitational fields accessible to observation. So far, the images match the predictions of general relativity with impressive precision. But as the technology improves, as the resolution increases and the sensitivity grows, we may find deviations from the predictions, hints of quantum gravity effects, clues pointing toward the deeper theory we're searching for. The black hole at the center of our own galaxy, Sagittarius A star, is particularly interesting. We've been studying the orbits of stars near it for decades. The star S2, which we mentioned earlier, orbits Sagittarius A star in 16 years and has been observed through multiple complete orbits. Its orbit traces the gravitational field with such precision that we've confirmed the mass of Sagittarius A star to within a fraction of a percent. And we've detected subtle relativistic precession of its orbit, exactly as general relativity predicts. We are measuring general relativity in the strong field limit, directly in our own galactic backyard. The Event Horizon Telescope's image of Sagittarius A star confirmed the black hole's mass from the size of the shadow, consistent with the mass determined from stellar orbits. Two completely independent methods agreeing to high precision on the properties of the same object. This is what science looks like when it's working. We fall into a black hole to understand it. But falling into a black hole also confronts us with questions that are bigger than physics. A black hole is a place where the information about your existence, the specific quantum state that made you uniquely you, enters the event horizon and may or may not survive. If it doesn't survive, if Hawking radiation really is perfectly thermal and information really is destroyed, then there is a sense in which you have vanished from the universe, absolutely. Not just that you have died and your atoms have dispersed, but that the specific pattern that was you, the quantum information that distinguished you from any other possible arrangement of matter, has been annihilated, erased, not transformed or dispersed, but genuinely destroyed. If it does survive, encoded somehow in the subtle correlations of the Hawking radiation that emerges from the black hole over billions of years, then you persist in some sense. Not in any form that resembles a person, not in any way that retains consciousness or continuity. But the information that constituted you is preserved in the universe's quantum state. Neither outcome is particularly comforting from a human perspective. But the difference between them matters enormously for our understanding of how the universe works at the most fundamental level. There is something philosophically important in the fact that the laws of physics are fighting over whether you can be truly destroyed. Quantum mechanics says no. General relativity says the singularity says yes. The universe is running a deeply fundamental argument about whether information, about whether what makes things what they are, is ultimately conserved. We don't know the answer, but the argument is being pursued with extraordinary tools and extraordinary minds. And the answer, when it comes, will tell us something profound about the nature of reality. Black holes are where the universe is most extreme. They're where physics breaks down and where new physics must emerge. They're where our two best theories of nature contradict each other most starkly. They're where the future of our understanding lies. And in a very real sense, every black hole is an argument the universe is having with itself about what is ultimately real. Let's return one final time to you, falling. You have crossed the event horizon. The universe outside is compressed into a shrinking bright region above you. Tidal forces are growing. The singularity is your future in the most literal possible sense. You are falling through the geometry of space-time in a region no human has ever been. In a way, no human has ever experienced. The physics here is not just different from everyday experience. It is more different from everyday experience than anything else the universe contains. More extreme than the interior of a star. More extreme than the moment of the Big Bang that we can still describe with physics. The singularity is where all description ends. And in that falling, in that approach to the edge of what the universe allows us to describe, something worth remembering is this. The black hole was not always a black hole. It was once a star. It burned for millions of years, fusing hydrogen into helium, helium into carbon, carbon through a chain of reactions into iron. It synthesized elements in its core. When it died, it scattered those elements across the galaxy. Those elements became new molecular clouds. New stars formed from them. Planets formed. And on some of those planets, possibly, atoms from that ancient star found their way into living things. The black hole you are falling into was once a star that perhaps seeded the universe with the raw material of life. And now it has collapsed. It has reached the most extreme possible state that matter can achieve. It has curved space-time around itself so severely that nothing escapes. It is evaporating, slowly, through the quantum fluctuations of the vacuum, returning its energy to the universe on a timescale so vast it makes the current age of the universe seem like a brief moment. And you are falling through its event horizon, through its interior, toward the singularity, witnessing the universe at its most extreme, its most broken, its most honest about its own incompleteness. There is something beautiful in that. Even in the context of destruction, even in the context of the unknown, the universe is not fully described. Our understanding is not complete. There are places where our theories fail, where our equations produce infinities, where the reality underneath must be doing something we can't yet describe. And those places are not obstacles. They are destinations. They are where the next understanding will come from. We fall into the black hole not just as a thought experiment in physics. We fall into it as an act of inquiry, as a confrontation with what we don't know, as a commitment to keep asking even when the answers aren't available yet. The universe has black holes. Black holes have horizons beyond which information may or may not escape. Horizons surround singularities where our physics breaks down. That breakdown is telling us something. We just haven't fully heard what it's saying yet. You cross the horizon and you vanish from view. Your friend watches from 1,000,000 kilometers away and sees you slow, redden, dim, and freeze at the edge forever. Or apparently forever. Eventually, even that frozen image will fade as Hawking radiation drains the black hole's mass and space-time changes. But while you were visible, you were one of the most fascinating and extreme objects your friend ever saw. A person at this edge of physics. A person at the boundary between what can be described and what cannot. Tonight, somewhere in the observable universe, two black holes are merging. The gravitational waves from that merger will travel outward at the speed of light, expanding as a ripple in the fabric of space-time itself, carrying information about the event encoded in the curvature of space, through billions of light years of vacuum, possibly eventually washing over Earth, distorting it by a distance far smaller than an atom, detectable only by the most sensitive instruments our civilization has ever built. And somewhere else in the universe, tonight, an accretion disk is blazing around a supermassive black hole at the center of a galaxy we haven't discovered yet. The light from that disk is traveling toward us through the expanding universe, red-shifting as it travels, and will reach our descendants' telescopes in the far future, giving them information about conditions in a galaxy that no longer exists in the form it had when that light departed. And at the center of our own galaxy, 26,000 light-years away, Sagittarius A star sits in relative quiet. Stars orbit it. Some of them have elliptical orbits that bring them within light hours of the event horizon. The gravitational waves from those orbits will eventually be detectable by future space-based observatories. We will hear those stars singing around their black hole in the language of curved space-time. When you look up at the night sky tonight, the center of the Milky Way is in the direction of the constellation Sagittarius, visible from the southern hemisphere in the summer sky. You can't see Sagittarius A star itself. The dust between here and there blocks the visible light. But it's there. 4 million solar masses of black hole, its event horizon about 24 million kilometers across, orbited by stars that have been teaching us general relativity for decades. It has never threatened us. At 26,000 light-years, it is too far away to affect us in any meaningful way. Our sun is in no danger of being consumed. The gravitational influence of the galactic center on our solar system is part of the large-scale gravitational field that keeps us orbiting the galaxy, nothing more dramatic. But it's there. The most extreme object most of us will ever live near. A place where time slows to a stop from the outside. A place where the inside has a future that terminates at the unknown. A place where two great theories of physics fight each other to a contradiction, demanding a resolution we haven't yet found. We know it's there. We have photographed it. We have watched stars orbit it. We have measured its mass. We have watched it flicker as matter falls into it. We have not yet understood it. And that is the most exciting thing about it. Thank you for falling with me tonight into one of the most extreme objects the universe has produced. If this changed how you think about gravity, about time, about the nature of the universe, please take a moment to like the video and subscribe to the channel. These deep explorations take real care to put together, and your support makes them possible. The next time you look up at the sky, remember that somewhere in the observable universe, events are happening that our best physics cannot fully describe. Singularities are terminating paths through space-time. Hawking radiation is slowly draining mass from ancient black holes. Information is being debated at the quantum level about whether it survives the most extreme processes the universe has ever produced. And somewhere, something is falling. Sleep well, under a sky full of stars that were born and will die, and some of which will leave behind the most extreme objects the universe is capable of producing. The black holes are out there, and we are still learning what they mean.